we call it a technology readiness level from 0 to anything up to 4, we take it. If we call of a research boards, 4 research boards like Aeronautical Research Board, Armament Research Board, Naval Research Board, Life Science Research Board, these research boards proposals are mostly top down, means what DRDO needs, we try to do that. Even if some proposal comes, that also we take it, provided it is linked to that particular specific projects or programs. We have also an industry interface, we call it a technology development fund. Recently, our government has supported this fund because to make our Make in India more stronger. So this we call it as a technology development fund, where specifically the micro, small and medium industries can be funded to do any research work. This scheme is already operational and it is available in our DRDO website. The proposals has been given. Any other proposals are also welcome from any industry, provided it meets the DRDO's projects, programs and aligned towards our requirement. That is the only constraint we are having. I'll just take on for 2-3 minutes. We have created some centers of excellence. I'll just tell all those centers. We have, in this directed research mode, we have created 7 centers of excellence as on date. The first center of excellence was Center of Propulsion Technology, which has been created at IIT Madras and IIT Bombay. This centers deals with the targeted deliverables of aeronautical systems in terms of engine development. So 4 technology verticals we have identified for that, including the gas turbine propulsion, hypersonic propulsion, solid liquid propellant modeling and morphing technologies. We have one more center created at Kolkata called Jagadish Chandra Bose Center of Advanced Technology. As you might have observed in yesterday's our Honorable Prime Minister's talks, he was talking of the future technologies related to India in terms of cyberspace, in terms of robotics, in terms of platforms. So to target some of these in terms of robotics, in terms of cognitive systems, we have developed this center in directed energy weapons. We have set up one more center at IIT Delhi called Joint Advanced Technology Center. This is basically for advanced ballistics, special structures, electromagnetic devices, terahertz, smart and intelligent textiles, brain-computer interface to enable the specific our future robotics technologies, robotics warfare, robotics systems, humanoid, exoskeletons, all these things we are targeting in these systems. Advanced Center of High Energy Materials in University of Hyderabad we are already having. We have a DRDO Center of Life Science in Coimbatore. We have a Research and Innovation Center at IIT Madras. I do not have much time to talk. I'll just only one example I will take. Suppose I am taking example of small turbofan engine. What we do is, this is a part of Center of Propulsion Technology. In the small turbofan engine, if we take as a specific example, this is my last presentation, I will not go for that. In the small turbofan development engine, if we say we have various technologies domain, like aerothermodynamics, ducts, fans, compressors, turbines, combustor, fuel, structures, rotor dynamics. Out of all these things, if we see, we have identified what are the areas we are lagging, research projects. Our gap was understanding of flow physics and loss mechanisms in small engine. We have launched project in this directions, many projects, loss reduction in shape ducts. Anyway, this is only a concept, I will not go because I have only 14 finished, I have 45 more, I will not go into that more details. Thanks very much. If you have any questions in terms of technology, trialing of DRDO, of anything or anything what I told or anything you want to know, please say.
Thank you, Dr. Rahman, for an excellent presentation, giving various thoughts of you, how we can pursue the R&D with various academic institutes. Thank you. I present a memento to you on behalf of the Indian Science Congress. Next speaker is Dr. G. Atidhan. He is again a eminent scientist, distinguished scientist from DRDO. He is the Director General of Microelectronic Devices and Computational Systems, a scientist who has worked on many microelectronic devices, cyber systems, information technology, information security, and many things. And let me tell you, and he has his PhD from IIT Mumbai in physics, and then worked on varieties of areas, what I have said. And is one scientist who gets into details very thoroughly himself and goes through minutely, and then only any topic what he says he gets convinced or allows. In fact, when I am chairing a cipher policy committee meeting, I actually, first question I ask is Dr. G. Atidhan is there, then only let us have the meeting. So such is the confidence what we have, and over to Dr. G. Atidhan.
Firstly, thank you very much, sir, for the kind and elaborate introduction, personal introduction. Dr. Reddy and Dr. Verma and the senior colleagues of mine from DRDO and the students and ladies and gentlemen. This is indeed an opportunity for me to share some interesting new ideas being pursued in my cluster. But before I proceed further, I would like to thank the organizers and also even compliment them for the efforts. It's not very easy, to organize such a big event, and really huge compliments to them. One small disclaimer before I start. Much of the ideas that I'll be discussing with you today are being developed, experimented in my laboratories in the cluster, Med&Cos and the CS cluster. And I don't claim any originality to them, but I am their spokesperson. You can say I am an integrator, of their ideas, and I present them for potential customers like you. Now, the title of the talk is Network-Centric Defense in the Age of Information Technology. When I was asked to prepare for a talk, I thought it should be really in the frontier area, looking ahead, instead of focusing on what we are actually currently doing, because what we are currently doing is productize and deliver something that our customers require immediately, urgently. But at the same time, we will also look ahead and see what new things we have to do, short term, middle term, and long term. So this idea that I'm going to explain to you today is perhaps a very long term idea, but you will, I hope, find it quite interesting. Now, so there is this notion called information age. Of course, we all agree that we live in the so-called information technology dominated age. Every day we connect to internet, we download, we see mails, we do our activities on the net. In fact, without net, many of us cannot conceive our lives today. Net with a lot of software and a lot of intelligence. But can we say the information age has arrived? There was an age, earlier called industrial age. So what was the clear marker of the industrial age? And can we, in fact, learn something from there and then decide whether we are in the information age at all today? So we will see, as the cartoon says, one guy says, the newspaper tells him that we are in the information age, the other guy doesn't know. At the end of the talk, I'm sure we'll figure out which age we are. So this is going to be a rough overview of my talk. We'll start with some deciders for warfare, for winning. Ultimately, in DRDO, we try to develop systems immediately required and maybe required long term for enabling our armed forces to prevail against our adversaries. So what are the deciders? That we will have to see. There are new concepts. One of them is this network-centric defense or network-centric warfare. Now, this one has been around for the last, I would say, decade and more. It was originally coined by one colonel from the American military called Boyd. But then, it's such a complex thing. It's almost like the proverbial elephant that different people, in fact, interpret it differently. So we will have to see whether we can come out with a new interpretation. And in the process of, in fact, trying to understand on our own terms what is this net-centric or network-centric defense or warfare, we may find that there are some very good models for, first of all, understanding the concept better and then even implementing it. That's what I would like you to understand. Now let's see what are the deciders for winning, as told by some ancient scholars. So there is this famous Sun Tzu, some of you might have heard about him. He is treatise, a great book called Art of War. This is highly quoted in military seminars and defense seminars. According to him, there is a matrix, which is shown there. So there is this knowledge that is key to winning, but knowledge of what? Knowledge of yourself and knowledge of your adversary. Both are equally important. And here the knowledge actually should include information about enemy's assets as well as your assets, and his capabilities as well as your capabilities. But then this matrix is very, very simple, very basic. It assumes either you have 100% knowledge or 50% knowledge or 0% knowledge, but there is a lot in between. And your own knowledge may not be total, your knowledge about the enemy may not be total. So this matrix obviously has to be expanded depending on the actual amount of knowledge about yourself and about your enemy you have. I will not interpret this matrix, I leave it to you. But our own saint one, Thiruvallur in Tamil Nadu, long back, about 1500 years ago, he has said, it's fine, our knowledge is fine, but we need actually a leader in whose head the knowledge actually is residing and who can practically apply that knowledge to lead his team to victory in war. So he says mind of the commander is key to winning. So that's a very important point to note. Now I said this knowledge is important, and then mind of the commander is important, going by whatever our pundits have said from the past. One of the things that comes to our mind when we talk about knowledge and information is the so-called common operating picture. As we can see, it gives you some rough idea of what are the basic details that the commander of forces must have. So basically he has to have complete information about his own assets and their actual distribution, and what assets he has in stock and what assets he can quickly create. All this he has to have. And the second thing is that this information must be shared. It should be commonly available to all the force units, right down to the last soldier, to the extent that he needs to know. That is why it is called a common operating picture. But at the same time, this picture should also include what our enemy has. That has to be also identified and then integrated into this common operating picture. Now together, this information has to be also continuously updated. In this context, in fact, I remember some very legendary observation of a famous scientist by name Laplace. Some of you might have heard about him. He lived in the glory days of Newtonian dynamics, and he was in the court of Napoleon. And Napoleon, as you know, was a great general, war general. So he proudly said, this Laplace, when Napoleon asked, what is your outlook, how do you support warfare from your angle? He said at that time, well, if I know the positions and momentum of all the particles on earth, in the universe, using my own laws and Newton's laws, I can predict any future time very accurately. The only requirement is that I should know the positions and momentum very accurately. Of course, that is where the catch is, but it is not possible for anyone to know. Perhaps with some massive supercomputers it might be possible, but then that's what he said. If I know all the positions and momenta of all particles in the universe, then I can predict any future state without any problem, with full accuracy. because the laws were clearly known. What were not known were actually the input data. The laws were knowledge, the input data in fact were required to use that knowledge to project into future. But a similar thing can be applied if you know your own assets and enemies' assets. Here we are not talking about particles, we are talking about actually macroscopic defense objects and their basic mechanics and their dynamic behavior, etc., and the nature of usage, exactly how they will be fielded. So if this knowledge is available, with a much smaller number of entities to be handled, certainly a simulation system should be able to project this entire common operating picture into its future. So this possibility actually, in my opinion, theoretically at least, exists. So we go to now models. When we talk about common operating picture, there are two sides. One is yourself, the blue force. The other side is the red force, your adversary. So you have to have some models. Games are, of course, natural models. You also know about chess as a game. Chess gives you the fundamentals of how you can fight against an opponent. In fact, if you study chess very carefully, you will find correspondence between the elements in the world of chess and the elements in the actual battlefield. It starts with the theater of war, which is nothing but the board, etc. The tactics and strategies are what are the moves. But the so-called net-centric system, what it could be, obviously it has to be the player's mind. So we are gradually, getting into that complex object, which we should understand before we can, in fact, implement out of that mind a network-centric defense system or operation system. But of course, there is one famous observation of von Neumann. He said, chess actually is not a game, it is actually a computation. He said if he knows any particular position for winning, the next positions and all can be very accurately calculated based on some objective function. Those of you who are computer scientists here would understand what I'm saying. But even though he said that, as far as humans are concerned, chess is still actually a game. When we talk about this common operating picture, first you will have to get the sensory data, you will have to fuse them, and then after fusing, getting the operational picture, you will have to also do what is called the situation assessment. And after that assessment, you have to do resource planning and then tasking. And while you are doing all this using computers, obviously, you'll have to take care of cyber security. So these are very important objectives or concerns when you are trying to develop a network-centric system. Conventional understanding of a network-centric system starts with the sensor grid, and then you have the communication grid, and you have the information grid where the decision making happens, and then the weapon grid. So normally one talks about these four grids. And you also have what is called this OODA loop. That is O for observe, O for orient, D for decide, and A for act. OODA loop as it is called. This also was created by same kernel as part of his approach of net-centric defense. So we will have to in fact pay attention to all that. But when this gentleman Boyd was talking about net-centric system, what did he have in mind? What was he intuiting? Network actually is a distributed entity, whereas center is a point. So how can you say you are developing a network-centric system? Actually, I think though it is a geometric contradiction, there is a simple resolution. If we talk about human mind, it's basically a network of neurons. Neurons are all interconnected, as we will shortly see in some other slides. And basically, the brain is a gigantic graph, network in fact. But then we don't see the individual elements. When we use the brain, it actually behaves like a super organism. So that is how, the resolution happens. There is no real contradiction. Yes, it is a network, but it behaves as a super organism. Now, that means the whole actually has to be greater than the sum of the parts. Because when we put lots of small pieces together, you get a whole organism. But the organism as such actually is more than the sum of the parts. So exactly how much more is the sum of the parts? That question has been answered by one famous strategist by name Metcalfe. He says, in the case of this kind of networked entities, the power of such an entity grows quadratically. That is, if you take a simple sum of n entities, the power is n. But if you actually network all of them, then the power is n square. So there's a whole world of difference between power n and power n square. So this is a very important message for designers of network-centric defense system. So when you network and when entities trust each other, then together their power actually grows quadratic. And this is a very important insight to keep in mind. So when you look at all this, now we come to the point whether all this can be handled successfully in individual commander's mind. So there is in fact some meeting, as the cartoon says here, there are so many branches, so many stages, and obviously, it cannot be done in the mind. We will have to go to the computers. Today's computers would be able to do it, perhaps not. So we will have to see how, in fact, we have to think of some supercomputers. Life technology has been imitating life. This is an example of a sonar. We have created aircrafts. So how much time do I take? So I'm in fact now basically coming to the main point of my talk. So the basic idea is, can brain be the inspiration for a network-centric system? So there are many observations about brain. There are a couple of very interesting observations. Without qualification, it's the most highly and most intricately organized matter in the universe. And there are some macroscopic points, like it weighs about 1400 grams and 10,000 genes, in fact, determine its organizations, etc. And this is a very interesting slide. You have to look at this. So it shows, in fact, the relative sizes of the brain, from the animal brain as it is evolved to the human level. From this picture, you can get a rough idea that over 200 million years, the shark brain, or maybe the fish brain, has evolved to the current brain. And you can say linearly it has increased by about a factor of 8. So it has become 8 cube times from the original size. Of course, you may say bigger animals have bigger brains, etc. But taking that into account also, one can say the human brain actually is the biggest brain of all the living creatures in terms of the brain size to the body size ratio. But as I said, basically the sizes increase linearly by a factor of 8. Now this has happened over a period of 200 million years. So we are not going to wait for the next super brain to be created by biological evolution. And we will have to take this job in our hand, and we will have to see whether using computing, communications, and storage technologies, whether we can actually achieve this outside the domain of biology. So I was talking about industrial age. One important marker of the industrial age is that there was force multiplication. Things which we were doing, we could do using machines much more effectively. There were machines which could lift things much more powerfully, much more quickly, and there were machines which could in fact transport things much more powerfully than us. So basically we could amplify our muscles. That was what primarily happened during industrial age. Now if you are talking about information age, you'll have to ask the question, are we having systems that actually have amplified our mind? I would say the jury is out. You have to still see how effectively whatever the human mind is doing can be done by an independent computer, however big it is, however huge storage capacity is. That is a challenge. In my opinion, we are at the beginning of the information age, but we have still a long way to go. Now, I'll skip some of these slides for lack of time. Well, we'll have to in fact start understanding how human memory works. That is the first step. And then how language works, language making in our mind. Briefly, in fact, I would like to mention these two things to you. In the 1950s, 40s, 50s, there was this debate between behaviorism and innatism. behaviorism projected that the human mind actually is a black box and it takes input and then converts that into output. Of course, this black box is decided based on learning or training. Once you train yourself, you acquire a certain black box to deal with input corresponding to that black box, and you produce output. But then came along this Chomsky and he said, no, brain is more complex than that. It is just not that we have black boxes, but we also have space to store data, and the function f that transforms input to output is not just fixed, but it is actually something that varies depending on the immediate past. That is, the immediate past data also can decide how in fact the transformation really will give the final result. So his idea prevailed, and finally we have a decent understanding of how language processing happens in the mind. There is one example given here. So when we are talking about this net-centric system inspired by brain, the first important thing we'll have to do is we should be able to process text data as intelligently as human brain does. So there are a list of things here in the red box. All these things we should be able to do. Now this we can do either using neurons and interconnections or using conventional methods which are actually available in computers today, but we'll have to scale them up. This is another example of a grammar which could be the basis. But I come to the final important faculty. Even today it's a far cry for computers to see any image and any video and then give you a complete list of identities of the objects, and maybe even tell you what are the activities happening in a given video. So this is where currently in fact we have to focus. There are some efforts in fact to recognize objects, but I would say still we are scratching the surface. I propose that basically you will have to finalize a representation which is based on maybe a graph, maybe some kind of a network again, because the brain itself is a network, as I said. So any given scene first should be converted into edges, as you see here, and also maybe converted into points or vertices. There are methods to do these things. And then you come to final graph representation. You just check all the edges and see what corners or what points are voting for them, because you have got independently points also. Similarly, you have points and then you see which points are voted by which set of edges. So in an iterative manner, you can come to a final representation, graph representation of a given scene. So if you have a huge database of graphical representations of all real-world objects, then by correlating that database with your graphical representation of a given scene, you should be able to identify all the objects. That is what is basically required for creating the common operating picture. Now, this actually gives you a complete list of building blocks required. I mentioned 2 of them. There are many other things like common sense reasoning, data mining, geographical information system, and information validation. So you cannot just accept whatever information comes to you as final. You will have to see how you have to validate them. That's where common sense reasoning will be useful. Now, we have to put all these pieces together, and as you can see here, we have force advantage. We have machines, which can do what we want them to do by controlling them. But we will have to also get what is called information advantage over our adversaries. We have to have better information, more accurate information than them. But we also have to have better cognition of what we have. That is basically the cognitive advantage that this particular diagram talks about. So if we put all these things together, then we might have what is called the network-centric defense system that can help us prevail over our adversaries. But this calls for what is meant by developing the machine brain. So whenever any complex technology like machine brain or anything is proposed, there will be always some reluctance. So we will have to overcome this. And there will be a lot of stakeholders who may not be able to appreciate. And we will have to patiently explain to them and then take our technology age to the next stage, which is information age. With this, I thank you once again for your patient listening. And I thank the chair and co-chair for this valuable opportunity. Thank you very much.
Thank you, Dr. Athajan. Excellent talk. Sorry, actually we need a lot of time to listen to this. Probably I will sit with you personally and go through the presentation. Thank you very much. We present a memento to you on behalf of Indian Science Congress once again. Thank you. We have a small submission. We have one more eminent scientist here who is present among us, Dr. Subhash Chandra. He is a distinguished scientist from DRDO. In fact, seeing him here, then I personally requested him to give a brief talk. One of the eminent scientists whom I have seen, who works on materials, propulsion technologies, high energy materials. In fact, I have a lot of personal regards and respect for him, and I request Dr. Subhash Chandra, whom I just asked about 1 hour back, to give a small talk on this. I have told the co-chair also about it, Dr. Subhash Chandra.
A very good afternoon, Dr. Reddy, Professor Verma, my colleagues from DRDO, and ladies and gentlemen. Actually, a talk about propulsion, I start at a disadvantage because most of the time the highlight of such a presentation is the videos which show how a propulsion system works. You might have seen missile flights in TV or maybe in the videos in YouTube. The highlight of such things is essentially the sound and light show that you see, and that's where the propulsion comes in. But talking about propulsion, I will confine my talk to the propulsion that we make use of in our missile systems, because propulsion essentially is a way of transporting something from one place to another. Now, when I mention this, I will talk about what we do in the case of missiles. Now, just to give an idea, you might have seen the missiles on display at our exposition. The missiles vary in size from 200 millimeters to maybe 2 meters, this is 2000 meters. The same thing goes in terms of the kind of thrust that is produced. It's from a few kgs to hundreds of tons. The missiles have a specific requirement that they need to work at extreme conditions, especially the tactical missiles which are used in the battlefield have to work in extreme weather conditions, in rain, sunshine, in temperatures varying from minus 40 degrees Celsius, especially for air-launched missiles, to plus 55 to plus 60 degrees Celsius. All these mean that the design of these missile propulsion systems have to work within a certain margin, and that's where really the challenge comes. Now, when you talk about missiles, again, we have missiles which perform different functions. They could be, surface to surface, or surface to air, or air to surface. The idea of, as I mentioned, of the propulsion system for missile is essentially to carry the payload from the point where you want to launch it to the point where you want to take it. That's where your enemy or the system that you want to damage or destroy is. When we come to I'll just briefly mention the way we divide our propulsion system. First of all, let me say that so far the most effective propulsion system that has been used in missiles is chemical propulsion. That means the energy comes from the breaking or comes from the combustion of the fuel and an oxidizer. The oxidizer could be some oxidizer which is present in the fuel, or it could be something which is like the air itself. So this is what has been really been the proven technology. There are other kind of systems, energy systems like nuclear or solar, which are used, for example, in electrical power systems in satellites. But they are not of much use here because of the thrust levels that they can generate. They are pretty low, though they are very efficient. Now, talking about propulsion, we can divide them into the kind of fuels that are used. We have propulsion systems where the fuel is a solid, where essentially, when I say fuel, okay, it's something that burns and produces hot gases, which when expelled through what we call a nozzle, it's essentially a tube through which the gases exhaust. It's a variable area tube, and that produces the thrust. What really happens is that, I think those of you who are mechanical engineers, they may know that basically when we say temperature, it's in a gas especially, it's nothing but the random kinetic energy that's available with the gas. So what we do essentially is that we take this random kinetic energy, that means the velocity could be in any direction, and on the average there is no specific direction. And when we pass it through this tube, we are giving it a direction. So what happens is that the random nature comes down, that means the temperature comes down, but the kinetic energy in a particular direction increases. And that's what gives the momentum for the gases to be thrown out, and that is what produces the thrust that we make use of. It is true not only for rockets, but also for air breathing systems. All this is chemical, mainly all the chemical thrust producing systems work in this way. So the fuel could be in the solid mode, where we could have a fuel where the fuel which can burn with an oxidizer, they are mixed together. They are one single piece. It could be that we also have systems wherein the fuel and the oxidizer are separated, and they come together only when you want to make them work, react, or combust together. So this is primarily liquid fuel systems. You might have seen the ISRO rocket motors. Some of their high efficiency rocket motors, like the cryogenic engine, is essentially a liquid fuel engine, whereas the solid rockets are used for the initial thrust. We also make use of air breathing engines. We make use of the standard air breathing engines are the turbojets, turbofans, which are used in our commercial aircrafts as well as in our fighters, but they are also used in small missiles. You may see some of them, for example, in the Rustam or in our cruise missile, they are used. As well as other air breathing systems like ramjets. They are called ramjets because they don't make use of the compressor which is used in a standard turbofan engine or a turbojet engine, and they work at supersonic speeds, and also scramjets, supersonic combustion ramjets. These are some of the things that are used in the missiles other than the rocket systems. Now, talking about the technologies that are involved, I would say that propulsion essentially derives its strength from almost all disciplines, both pure sciences as well as applied sciences and engineering, I think, except for maybe nuclear energy, so at least so far. It derives, it needs information from all these cases. For example, we need to make structures which can operate as a rocket. The pressure under which these rockets operate, inside pressure, can vary from something like 50 times the atmospheric pressure to, in some very specific cases, to 500 times the atmospheric pressure. The temperatures can vary from something like 2000, 1500, let's say in the case of gas generators, to 3500 and beyond. So you can see the extremes of conditions under which the materials have to be, essentially confine these hot gases. So we make use of high strength materials. Today we are using a lot of metals, metal alloys. We also use composite materials, carbon fiber with some sort of an epoxy resin. But these are areas where we need still more, let us say, information or research to improve these materials, to make them lighter, to make them fail gracefully. For example, it should not explode. If our design criteria, what we would desire to have is that even if there is a damage, let it leak, but let it not explode, because that can cause a significant problem for the people who handle this or the structures which are nearby. We have not still reached such stage, but this is something that we would look for. Similarly, when something hits this, let's say that in a battlefield, let's say a bullet hits this, it should not explode. If it just burns, it's okay. Or if there is a fire around it, if the casing could somehow unravel itself and then just allow the gases to leak, that would be the best thing. So these are some of the research areas that I would say are in the leading phase in our area. As I mentioned, one difference between our systems and, for example, other commercial launch vehicles is that when we make a system, a missile for example, we assemble it, we put it inside a casing, and like one of the earlier, I think it was a Hero moped when first came, they said fill it and forget it. So we do exactly that. we have to just load it, and almost, at least the propulsion system is concerned, there is no way to check its health. And for after 10 years, when the soldier pushes the button, it has to work. So the kind of reliability that is required, and for a one-time application, this is the thing which makes it different from other rocket systems, especially those which are used in the commercial area. So we need to know how each one of these materials behave as they age, what kind of deterioration in performance can happen, and this we need to know without the knowledge that 10 years down the line what's going to happen. There are methods, but there are also limitations to such methods. The other thing is the combustion itself. I mentioned about, when we say that, okay, we see combustion, for example, in our house, in a stove, or when we burn firewood. But the actual phenomena that takes place inside is pretty complicated. Now, the question is that why do you need to know? I mean, to burn wood, why do you need to know the real detailed mechanism? You light it up and give it sufficient heat, it's going to start burning. But the thing is that there are many cases where we need to operate systems at their extreme limits. For example, you might have heard about lean combustion to reduce the temperature of combustion, so that this is true especially for commercial aircraft, so that the pollutants that will not be formed, or the amount of pollutants will be formed will be very less. But then this has a penalty in terms of the instability of combustion. It can blow out any time, okay, because of the stage of operation, and plus it can create instabilities, and that can create either oscillations of the combustor or cause a structural failure or even blowout of the combustor, which is not a desirable thing, especially for a missile system where you do not have such a control to relight it. Maybe in an aircraft you may have 1 or 2 chances for relighting, but we do not have. So this is another area why we really need to understand. If you take a solid fuel like a wood, what happens is that there is a phenomena by which the heat essentially heats up the wood, and there are materials which will pyrolyze or which will form gases, and these gases come out and burn. So there is a kind of combustion, burning taking place in a gaseous level, which in fact also drives a combustion in a solid level. The same thing happens in our case also. We have, when the propellant, when it is heated, it produces gases, and it will also have solid particles like hydrocarbons, or it could be even metals to increase the temperature. And these combustion phenomena we need to understand, because the combustion, there are problems associated with this. In an enclosed cavity, that is what we have in the case of a rocket, these enclosed cavities can have their own resonances because of the acoustics. And if somehow the combustion, let's say, resonates with this kind of at the frequencies, then it creates a very large feedback of energy from the combustion to the acoustics, and this has been a very severe problem, and it takes a lot of effort to control. And so this is still one of the areas, I believe, in fact, all over the world, people are doing a lot of work to understand what goes on over there, because there are a lot of physical phenomena taking place. Things will melt, and then it will bubble, it will produce gas, and many such things happen. Now, I have talked about the material. Now, you know that I talked about the very high temperatures. Now, you need to protect the casing, for which we use insulating materials. We use what we call ablative insulating materials, which essentially form gases which absorb energy. Now, design of these ablative materials is, again, because they are essentially not contributing to the energy to produce the thrust, but they are contributing to protect the casing. So it should be as light as possible. And we need to design very light, very efficient systems. You might have heard, one of the things which people have been using quite a lot is carbon phenolic systems. And now, if you read in NASA, for example, they have developed a foamy carbon phenolic system, which has reduced the mass, and they claim, in the case of Apollo spacecraft, when they re-entered, those insulation systems could be used only once. But now they claim these kind of insulations can be used 3 to 4 times. They can be repetitively used. So you see the amount of time and money saving that you will have. We also, because our systems have to be as light as possible, this is one of the areas that we need to work on and we need to prove. Now, coming to combustion, again, the way by which you have combustion, if the oxidizer and the fuel are kept separately in the form of gases or in the form of liquids, is essentially that, you spray these. Now, why do you spray this? Why do you need to spray? Why do you just pour them together and, you somehow light it? No, it doesn't work. The reason is that the combustion takes place at the interfaces between the oxidizer and fuel. So you need to produce a large interface. You need to produce large area. And the only way to do that is to form spray, so that you present a large area of these reactants together. Now, the spray, again, the spray formation, how a spray forms. There are a lot of engineering approximations to that, but we are looking at spray formation not only of just liquids alone, but if I have metals, for example, embedded in it, so that I can have a higher density and I can form a spray, so because of which I get more efficiency in combustion. So this is an area which is under a lot of, let's say, attention in our country as well as outside. Another thing is that even between gases, it's not very easy for them to burn. One of the problems in supersonic combustion is that when you have two gases, fuel and oxidizer, flowing together, they don't mix very well. Unlike the case of, if you look at your stove, it's essentially what we call a premixed combustion, because the air and the fuel mixes before it comes outside and burns, like your Bunsen burner. Okay, it's something like that. But we cannot have a Bunsen burner, because one of the things here is that the velocity with which these gases will mix in these conditions will be of the order of about 2 to 3 times the speed of sound. So if you want to give sufficient time for this, you need to give a very, very long combustor. So you need to have some methods by which you can mix this, and so that they can also react. Now, this is another area which is of very importance. Now, I'm just quoting a few things because I'm not really prepared for a specific talk, and I don't think the time is there for us to dwell in detail in this. But I would say, as I again said, in propulsion, I see all disciplines, whether it is mechanical engineering, whether it is chemistry, physics, whether it is electronics, everything, because we need to control all these things, for example. So everything has a part to play, and I believe that's one of the reasons why this field to me is very exciting. I will stop here, but I would say that those of you who are interested in this, please come to our exposition. You please engage us, talk to us, even criticize us, so that we will know from each other, and we need more of you in the future. Thank you.
Thank you, Dr. Swash. Excellent talk, even though we asked you about an hour back. Thank you very much. I present a memento from Indian Science Congress.
So, on behalf of the Indian Science Congress Association and the host, I take the privilege of presenting this memento to our chairman, Dr. Satish.
On behalf of the Indian Science Congress, I present a memento to the co-chair, Professor Verma. I take this opportunity. Thank you. I think we are running out of time. Anything like to say?
At the end, on behalf of Indian Science Congress Association and on behalf of the host, I thank the chairman, the speakers, and all the participants who took, who participated in the deliberations, and for their patience hearing. Thank you very much.
Thank you.
And we need more of you in the future. Thank you.
Thank you, Dr. Subhash. Excellent talk. Even though we asked you about an hour back, thank you very much. I present a memento from